Alright guys, so here we're on our last method, the balancing our half reactions in basic conditions. And so just again as we noted, somewhere in the problem it will note that you have a certain set of conditions. And so here we see the word basic written over our reaction arrow. Alright, and so it's really pretty similar to what we've just done with our acidic conditions. Again, you're going to go through, assign oxidation states, write your half reactions, balance all of your elements, then balance oxygen using water, balance hydrogen using protons, balance the charge with electrons, then when necessary multiply by an integer to get the electrons to be equal, then you add the half reactions together. But where it changes is after you add the half reactions together, you're probably going to be left with some protons floating around. But in a basic solution, we know what makes a base is that they love to come and grab hydrogen ions. And so that means that we're going to have to add our OH ions, our hydroxide, in the same amount as we have our H plus ions, our protons. So we look at whatever number of moles of H plus ions we have, and then we add the same number of moles of hydroxide ions to both sides. And this is key, guys, please don't forget, to both sides of the equation. But this will be a little easier to see as we work through. And then whenever you end up with your hydrogen ions and your hydroxide ions on the same side of the equation, we'll combine them to make water, because we have H2 and then O. Then again, we'll cancel identical species and give everything one last double check to make sure our number of atoms and our charges are appropriately balanced. Okay, so let's get to assigning some oxidation states. So I've already got a couple on here this time. So we know silver has an oxidation state of 0 since it's an element in its pure form. And this time oxygen will also have an oxidation state of 0 because it's an element in its pure form. Now I know normally we're used to oxygen having a -2 charge, but that's when it's involved in another compound. Here it is as dioxygen in its gaseous state, so it's its pure element, and so it likewise will have an oxidation state of 0. Now let's get to our friendly cyanide ion over here. And so this is where our electronegativity rules will come into play. And since our nitrogen is more electronegative than carbon, it will hold the negative oxidation state. And so let me see if I can pull up the periodic table for you guys here. Okay, there we go. So if we look here, we're used to assigning fluorine -1, oxygen -2, so that means nitrogen is going to be assigned a charge of -3. Alright, put this out of the way. So we'll assign it a charge of -3, and since the molecule has an overall -1 charge, carbon will be -2. Now let's look over here at this side of the equation. We see the cyanide again, and if we remember, this is one of our polyatomic ions, Cn-. And so the oxidation states of both nitrogen and carbon are not going to change. We're still going to have +2 for carbon and -3 for nitrogen. But if we'll notice, this will affect the oxidation state of silver, because this whole ion is -1, but there's 2 of them. So this whole part here, or compound, is -1. Alright, but if we'll notice, don't forget this guy over here, this whole thing has a -1 charge. Oops, I just wrote this wrong. So let me rewind and state that again. So this whole part, since there's 2 of a -1 polyatomic ion, is going to be -2. There we go. And so if we want our overall compound to have a charge of -1, we need to add a +1 with that -2 to get -1. Alrighty, so that tells us the oxidation state of silver here is +1. So just like before, we want to write our reduction and oxidation half reactions. Just going to label them because that kind of helps me keep everything straight. Alright, and just to, oops, turn the camera, sorry. And just to remind ourselves, as is very good to do, in reduction we are gaining electrons, and in oxidation we are losing electrons. Okay, so let's start and see what we can do. So silver here is going from an oxidation state of 0 to +1. So its oxidation state is becoming more positive, so that means it's losing those negatively charged electrons. So that means it's going to be our oxidation half reaction. So let's just go ahead and write that. And since cyanide is involved in making the product, it's also going to be included here in our oxidation half reaction. Okay, so there we go, got our oxidation. And now for our reduction, oxygen is the only thing that's left. And it doesn't have anything to pair with it quite yet, but we'll fix that in a moment. So we'll just write it as a reduction reaction for right now. Okay, so we've got an oxidation states, half reactions. Now let's balance some elements. So our silver is balanced 1 and 1, but our carbon, we have 2 here and only 1 here. So let's multiply this by 2, and that should fix our nitrogen as well, and it does. 2 nitrogens and 2 nitrogens. Okay, so we've done that, balanced our elements. Now we need to balance our oxygen using water. So no oxygens here, but here we go. So 2 oxygens here, so we should use 2 waters to balance it. So that gives us 2 oxygens here as well. So now we need to balance our hydrogens using H+. So again, no hydrogens in our oxidation reaction, but here we have 4 hydrogens, so we're going to add 4 protons to the opposite side. So now 4 hydrogens, 4 hydrogens. Check. Now we should balance our charge with our electrons. So here on this side we have a charge of +4, and this side is neutrally charged. So in order to cancel out that +4 charge, we should add 4 negatively charged electrons to this side. And that makes sense because in our reduction electron in our reduction reaction we're gaining electrons, so they should be on the reactant side. Now here on the bottom we have a charge of -2 on this side and only a charge of -1 on this side. So that means we need 1 more negatively charged electron on our product side. And that makes sense because this is our oxidation reaction, so we're losing electrons, so they should be on the product side. Alright, so good so far. So now let's check our number of electrons. Now if we notice, the reduction half reaction has 4 electrons, while our oxidation reaction only has 1. And so that's a problem because we need these guys to be equal. So we ask, okay, well what can we multiply them by to get them to be the same number? And in this case, we can just multiply 1 by 4. But that means this whole equation has to be multiplied by 4. Alright, so now we've done our multiplying. And so now let's line everything up and add our half reactions together. So I'm just going to rewrite what we have so that it can be a little more clear. So here we have 4 electrons. I'm just rewriting our reduction reaction. Down here, don't forget we've multiplied by 4. So that means this goes to 8 for our cyanide. Oops, forget that. There we go. See, I almost did that. But gotta remember that 4 in front of this 2 plus 4 electrons. Alrighty, give y'all a minute to copy that down right quick. Okay, oops, forgot to straight on water. There we go. Okay, so now let's add these guys together. Again, our electrons will cancel. 4 electrons on the reactant side cancels with 4 electrons on the product side. So now let's write our overall reaction for what we have. So we have 4Ag for silver plus 8Cn minus 2. So I'm just rewriting what hasn't canceled. The only thing that did cancel was our electrons. Everything else should be still hanging around. Let me zoom that out. Our equation's kind of getting long. It's hard to see. Okay, there we go. So at this point, we've added the half reactions together. And so the next step is to add the same number of hydroxides to each side as we have protons. So we'll come and see that put into action. Okay, let me grab a different color pen so we can help distinguish that. So if we notice, we have 4. Okay, so 4 moles of protons. So that means we need to add 4 moles of hydroxides to each side. So I'm just going to write those down there because we're kind of running out of room. Okay, so notice they're on both sides, not just one. So then now, step 6, so we've taken care of step 5. So now in step 6, we're going to combine our hydrogen protons with our hydroxides to make water. And that's just when they're on the same side. So here, these guys will combine to make water. Now in this case, we're fortunate because they're the same amount. But like for example, if you end up with 5 hydrogens and like 4 OHs on one side, then that means you're going to have 4 molecules of water and 1 mole of hydrogen protons left over. So you combine equal amounts to make water. So 4 and 4 gives you 4 molecules, or 4 moles of water. Alright, so now that we're combining, let's rewrite that. So now we've got 4Ag here's our water. Write that a little more neatly. You just disregard the scribbles. Sorry about that. Okay, so there we go. So y'all can see that. Okay, now if we're to look at our last step, it says cancel identical species. Kind of right up there at the top, I'll bring that down. So cancel identical species and then check. So if we notice, we do have some identical species on both sides. And that would be water. So here we have 4 waters and 2 waters. So if we're canceling identical species, we subtract 2 over here, and then that leaves us with 2 here, because this side had more than that side. Okay, so now for the final writing. Get excited. Try to write maybe a little smaller so we can fit everybody in. Here's our 2 remaining waters. Oxygen gas. Alright. Ta-da! Okay, and if we went back and checked, everything should line up. Here we have 4 silvers, 8 carbons, 8 carbons, 8 nitrogens, 8 nitrogens. Neater. Okay. 4 hydrogens, and 4 oxygens. 2 plus 2 equals 4 oxygens here. Our charges line up here as well. So we have a total charge of -8 over here from this guy right here. And then we have a charge of -8 over here as well, because we have 4 -1s times 4 -1s, and -4 plus -4 is -8. Alright, and that is how to balance using the balance a redox equation using the half reaction method in basic solution. Alrighty, thank you all.